take a look at the example problem here. So it says a force parallel to the x-axis produces a potential energy function of this, where x is in meters and u is in joules. Find the equation for force. Okay, well, in order to find the force equation, I need to take the negative derivative of this. So then my force equation is going to be negative 3x squared plus negative 16x, and then that goes to 0. So this is in newtons with x in meters. All right. Next, it wants me to find where are the equilibrium locations, and are they stable or unstable? Well, equilibrium locations means my force is 0. So when I see the word equilibrium, I know that force equals 0. That's the clue. So now I need to set this equation equal to 0. So I have the force equation is, and I'm going to factor out a negative x out of there. So I have negative x times 3x plus 16 here. And so this gives me two solutions for force 0. One of them is x equals 0. And the other one here, subtract 16 to the other side, divide by 3. My other x is negative 16 thirds. And those are both in meters. So those are my two equilibrium locations. Now to test to see if they are stable or unstable, let's hop over to the computer and graph those.
I have a cubic function and a plus 50 intercept. So when I go to my window here, I'm going to go from negative 10 to positive 5, so that'll have those 2 points of interest, the negative 5 thirds and the 0. I'm going to have to go from negative 10 to 200 to see this whole graph here. So when I graph this, I get this nice cubic function that I was looking for. I have my 2 points of interest. So now let's decide if they are stable or unstable. Let's head back to the board.
All right, so as we saw from the graph, and remember we have to graph the potential energy graph to see where it's stable and unstable, and we have the unstable locations at the tops of those peaks and the stable locations at the bottom of those peaks. Because whenever it's moved to a place like this, the slope is positive. That means that the force is negative, so it's pushing it back to that point. Here the slope is negative. Flip the sign, so the force is positive, so it's pushing it back. You can think about it almost like a hill. That, you know, if I put a ball at the bottom of the hill and I give it a little bump, it's going to stay in there. But if I balance it right there at the peak and I give it a little bump, it's going to go off and never come back. All right, the last part of this question, what is the most amount of total energy an object can have and be bound around a stable equilibrium location? Okay, so what we need to know is what is this energy value right here? Because if it has at this point, at x equals 0, the potential energy is 50. If I give it a little more kinetic energy, it's going to go up the wall a little bit and then come back down. So how much kinetic energy can I give it until it gets to this point? So whatever our total energy is here at this peak is going to be our maximum amount of energy. So we need to then go ahead and do U is equal to x cubed plus 8x squared plus 50, and figure out what that is at negative 5.3. All right, and we get, oh shoot, we didn't calculate that. Let me calculate that quick for us. Oh, that was good. 125.8 joules. So 125.8 joules. So any more energy than that, and we won't be bound in this area is what it's called. So we had 50 joules of potential energy, and so that means we have roughly 75.8 joules of kinetic energy when we're at the bottom. And as we go up, the potential energy gets bigger, the kinetic energy gets smaller, and so when it reaches this point, it will have no kinetic energy, and so it will come back down. You'd probably want a little less than that because that gets you right to the peak before you come back down. Okay, there you go.